Hello and welcome to the fourth lecture in our Maps, Images and Structure class, and today I'm going to be talking to you about folding. So the important thing we're going to learn here is about what sort of a shape, what the morphology of folds are, and what effect that has on the structure contours that we see on the map and that you're going to draw on the maps. And we're going to understand how folds are depicted on geological maps so that you can recognize them in the future when you look at real maps. And then subsequently we'll learn how to draw a fold in a cross section based on the data that you can glean from a geological map. So you may remember from the previous lectures that how we've been using structure contours, that they allow us to see how 3D surfaces behave and how they can be depicted on 2D maps, and we use structure contours to calculate the strike and the dip, and by comparing the structure contours with topographic contours we can predict outcrop patterns. And last but not least, we looked at how structure contours have a surface with a that generally speaking that they're uniform strike and dip, that they're parallel and they have a consistent spacing. That's what you were doing in the previous exercises. So for example, here you can see on the right here, this is a uniform dip. The structure contours are evenly spaced. There's the same spacing between each one. However, when the surface is not straight and flat, we see that the contours change their spacing. So this would be steep dipping and this is shallow dipping, and so this means that the surface is curving, it's been bent. And of course bending like that is part of the what we expect to see when we start looking at folds. So in a fold like this, for example, on the left side we see strata dipping away to the left, and here the strata are uniformly dipping. They're the same angle across here, so in this case the structure contours would be evenly spaced, and on the other side, although they would be dipping in the opposite, but you will see the fold itself is curved at the top, so we would also anticipate to see a change in the spacing of the structure contours across the top of the structure. So let's learn a few words about how people talk about folding and what the terminology of that would be. So, what is a fold? It's pretty obvious. It's a bend in the rock. It's a ductile sort of structure where you take a layered sequence and you bend it into a series of folds. And we can only see this because, of course, the rock itself is layered in the first place. It's definitely a ductile structure. If it was brittle, it wouldn't fold like that. It would break and we'd have a fault. And in general, folds are compressive structures. When you squeeze a sequence of sedimentary rocks in a horizontal direction, they're going to bend into a sequences of folds. So there are two basic styles of folding. There are antiforms, which form like an arch type structure, and there are synforms that show this sort of bowl type structure here. So yeah, if it's pointing upwards, it's an antiform. If it's pointing downwards, it's a synform. So these are similar to, but are different from, anticlines and synclines. So what the definition of a syncline is one where the oldest rock, number 1 here in red, is in the center of the structure, and they get younger towards the outside of the fold. So 4 would be the youngest and 1 would be the oldest. In contrast, a syncline is a bit different because that is the youngest one is in the middle and the oldest is on the outside. They young towards the center and anticlines young away from the center of the structure. So you might wonder why on earth that is different between the antiform and the anticline. Well, you have to have this younging direction for it to be an anticline. It is possible that if you folded a sequence of rocks that were already upside down, you could generate an antiform which would not be an anticline. Although in general, antiforms are usually anticlines, but not always. In some mountain belts, the sequences have all been turned upside down, and you can find the opposite. But for our purposes, most of our antiforms are going to be anticlines. So let's think about the different parts of a fold. When we start talking about folds, we should be aware about the different terminology used. First thing is the highly curved part, what I often call the nose of the fold. But here you can see a more appropriate name would be the axis or the hinge, which is running along the edge of the fold here. And the straight parts on either side are called the limbs of the fold. So what you can see here is a series of different shapes to the folds, and we use this terminology to tell the reader of your report or exam exactly how the geometry changes from one to the other. So if the angle between the limbs is very large, this is referred to as being a gentle fold. And then progressively, as that angle gets smaller and smaller, we use these terms open, close, tight, and if they're essentially parallel, then we call it an isoclinal fold. It's not necessary to memorize these degrees, but it's a general guide to be able to say whether the folds are open or tight, and some knowledge of that would be required. So when we come to measure the geometry of a fold, you have to measure the orientation of the limbs, but a critical feature here is the axial plane. So the axial plane passes through the hinge of the fold and is essentially has the same angle between the limbs and the axial plane. It passes right the way through the center of the fold in this sort of vertical direction, and it runs along the fold axis here. It gives us an impression about whether the fold is upright or reclined. The other thing that people measure is the orientation of the fold axis itself. Is it horizontal? Is it dipping? And in which direction is it dipping? And on the ground surface, which would be your geological map, we have this ornamentation that people show essentially to show where the axial plane is cutting the land surface, and that's called the axial trace. So again, folds can be nice and simple. They can be symmetrical, where they're the same on either side, like this, or they may be asymmetric, where there is the axial plane is not vertical, but the structure is inclined to one side, and that's a very useful feature because this gives us this so-called vergence direction. It gives us a sense of shear, which can be used to understand tectonic stresses and the direction in which rocks have been deformed and moved in the past. So vergence in asymmetric folds is very important for interpreting the geology, and they tend to be more common than the simple symmetrical folds. Indeed, if your axial plane is flopped right over like this, getting to be quite close to the horizontal, we call this overturning. You can see that this limb here is now essentially upside down. The younging direction is pointing downwards. That's a feature of overturning. If it continues to do that, of course, it'll be completely upside down, and then the axial plane would be horizontal. This is, again, shows a vergence direction, in this case towards the right. But this is a common feature of folds that you should be familiar with, the overturning. And I mentioned the fold axis. If the fold axis is not horizontal, we describe that as plunging, and the angle between the horizontal and the fold axis is known as the plunge. And that can be measured with a compass in the field, and you may be able to map this out using structure contours on a geological map as well. This is of course more common than perfectly horizontal. Rocks tend not to be perfectly horizontal. Yeah, and the plunge direction is the direction down dip, down the fold axis. Here's a little example of one where it's plunging in two directions. So we have some sort of anticline, and on the left side it's plunging left, and on the right side it's plunging right. And this is sometimes called a whaleback fold. Again, they're pretty common. Folds essentially don't go on forever. They have to end at some point, so they rarely are horizontal for many, many kilometers. They tend to plunge off into the subsurface. And again, another feature that we can describe when we're looking at folds is whether the fold is round or pointy, essentially. So here's an example of one that you will see on your Dorset field trip. Here the fold axis is rounded, and another example that, again, this one from southwest England as well. This is a chevron fold, what we call a chevron fold because the axis, the fold axis is very tight. It's a very small. These are straight limbs with a very limited. All the folding, all the bending is done in a very short space as opposed to a wide space on the right-hand example. So that's a tight. It's a isoclinal sort of. Oh, it's not an isoclinal fold. It's quite tight, and this one has a very pointy hinge axis. So, how are we going to spot these things on geological maps? Well, you can find distinctive patterns which are associated with folding. For example, if we have here an anticline with these coloured rocks, this red one is the oldest, and going up to a blue here is the youngest, green the next youngest, but this repeating pattern on a flat surface is suggestive of a fold. If you see that A, B, C, B, A, this repeating away from a central axis there, it suggests a fold. So in this fold, you can see the hinge, the axis of the fold. The hinge is horizontal. It's not plunging at all. The plunge is 0. If you, however, have a fold which is plunging, like so, where the fold axis is dipping down towards the right, you can see, well, what the outcrop looks like. So in this case, we see you still have the core, these red, orange coloured ones. Those are the oldest sediments. But you can also see this V-ing pattern. This is a flat surface, right? So if you get V-ing pattern on a flat surface, that's indicative of a fold and a plunging fold as well. And you can see that it's plunging in the direction in which the V is pointing. So we have to be a bit careful because you can get similar outcrop patterns from different types of topography. So for example, I mentioned how the strata repeat themselves when a fold is exposed on a flat surface, but you could also get the same map pattern if you had flat rocks and a bent topography, like a valley, right? With the oldest material at the bottom of the valley and the youngest at the top. And that on a map, that looks exactly the same. So you can only tell the difference between these if you look at the topographic contours. And that's why those are provided on most geological maps. Likewise, this hinge, the V shape that we derive from a plunging fold, I explained in the last example, that can also be generated on a geological map if the fold, if this case a not plunging fold, a horizontal fold, is intersected by dipping topography. And in this case, we get a V shape like that as well. So interpreting the patterns you see on the map, you have to take that with a pinch of salt. You have to look at the topography to make sure you really do have a plunging fold and not a horizontal one, because that is related to the topography, not the fold itself. So all of these issues can be addressed if we look at the structure contours, right? So we saw last week how the structure contours are change their spacing. In the case that we have a folded surface, you can see this example where we're going from 0 to 10 is a wide space, and then these 10 to 40 are tightly spaced, and then broader again between 40 and 50. And that tells us that this is like some sort of bent structure like this. It would be half of a fold that you might recognize on a geological map. And you can determine the dip on the strata with simple geometry here. The spacing between the structure contours can be used to calculate the dip on the fold limb. And a similar approach can be used with folds which are plunging. So that was a horizontal fold you saw in the last one. In this case, we have this bent blue surface which is plunging down towards the viewer in this case. And you can see how the structure contours here are changing around the fold. So this defines the geometry of the fold, and this bending of the structure contours is indicative of the presence of a fold. Again, you can use the spacing on the contours to determine the dip of each of these surfaces. If you look at the contours here compared to here, you'll be able to define the dip of each of the different limbs, and in doing so you define the plunge of the axis, the fold axis. So that's right, we look for variably spaced contours. And when you find a fold on a geological map, you need to mark that. And there is a way that geologists like to do this. We mark where the axial trace, that's where the fold axis is intersecting the land surface. And we can draw the attention of readers to the map, to the presence of a fold, by providing this sort of annotation, and that's something you're going to need to do in your exercises and exam work. So there is a defined terminology and the geologists use. Essentially, outward pointing arrows indicate an anticline or an antiform if they're not filled in like this, and conversely synclines are shown by inward pointing arrows. The arrows essentially pointing down dip. So if they point inwards, it must be a synform or a syncline, and outwards is an antiform or an anticline. And you would mark that on your map to show that you had identified that. So now let's think a little bit about folds in cross sections. This is something that you're going to be defining using the worked example this week, but you'll do this every time you see a geological map. Essentially, we can use the map interpretation to look at the geology of the subsurface, to define, to extrapolate curved surfaces into the subsurface. As this notes, it can be complicated because folding can be itself can be quite complicated, and we have to essentially do our best to take an educated guess about what's happening at depth with folded rocks. You can define this to some extent because of the constraints we have at the surface in terms of folding. And generally, geologists have a few basic rules of thumb that help to keep things more simple so you can make some progress. And quite often we assume that the thickness of any particular bed is the same thickness all the way around the fold hinge, like this, right? So this distance here remains the same, and that's something that you can use when you do your own work a little bit later this morning. So in general, what you're going to do is to do a little bit of extrapolating. You're going to use your knowledge of geological structures to fill in the bits that we don't know. So you can imagine, but you would plot structure contours for each of the limb surfaces to define a dipping structure here, and of course also on the right side of the structure. But you don't have any structure contours for the middle, but you know that since it's dipping left over here and right over there, that there must be a connection across the top, unless for some reason you think there's a fault there. So essentially you just have to fill that in, and we do that using this assumption of the equal thickness, right? So that the thickness of the bed at the hinge is the same as it is in the limbs. And you just have to infer that and use a little bit of artistic impression to try and make a reasonable interpretation of the structure based on your understanding of the limbs. So for example here, this is one that somebody's done already, where we're extrapolating both above and below the ground surface, and this is something we want you to do. You can see that the stuff that has been eroded away has been more gently coloured to emphasize the fact that it doesn't exist anymore. Firm colours in the subsurface here, and we're using those same annotations there to show the folding. This case would be a anticline, and this one a syncline, where we use it on the map surface and in the cross section. And essentially this line here is the intersection of the cross section with the axial plane. So this is where the axial plane is defined in the middle of each of these folds, and you can see they're dipping towards the left in this particular case. Yeah, should be careful. Don't only draw it above the unconformity. If there is an unconformity, then the fold, which would be below the unconformity, has to stay below the unconformity. You would only draw it above that if the unconformity itself was itself folded. So let's spend a minute or two here thinking about how we describe folds, to recap a little bit about what I've covered up to this point. So first things you're going to ask yourself is it an antiform or a synform? So in this case it is an antiform. And do we know anything about the relative ages of the rocks in the middle or the outside of the fold? Can we say if it's an anticline or a syncline? You can measure the angle between the two limbs, interlimb angle, that lets us know whether it's an open or a closed fold or a tight fold. We want to know if it's symmetrical or asymmetrical, and does it plunge? Does the fold, is it horizontal or does it plunge? And is there some vergence there, as there is in this case? It's just a gentle vergence towards the right. And once you've been able to do that, you can say something about the stress field in which the fold formed. Since a fold like this, an anticline like this, is relatively horizontal, we know that the primary compressive stress is also horizontal. This is termed sigma 1 and points in towards perpendicular to the fold axis. On the other hand, the vertical stress, sigma 3, which is essentially an extensional stress in most cases, would be vertically oriented, and that means that sigma 2, the intermediate stress here, is oriented along the fold axis. So we can use the geometry of the folds to identify the direction of compression, in this case sigma 1. So here's an example of that. We have some type of antiformal anticline. I guess you could just call it an anticline. It is antiformal, but anticline is good enough. We know that it's a fairly close fold because it's only got a moderate angle, 45 degrees. In this case, it's an asymmetric fold. It's not standing upright. One side of the fold is not a mirror image of the other. And so we see that because the fold axis is inclined, dipping towards the south, we know that the vergence of the structure is verging towards the north, and moreover the plunge here is towards the east. Yeah, and you can see here that the fold is involving A, B and C, but not D. This is a dike cutting across the section. So we know the folding must predate the intrusion of D, but postdate the sedimentation of C. So we have therefore we have some understanding of the geological evolution here, the direction of compression, the direction of tectonic transport, in this case towards the north, and we know roughly when that was happening. If you know the age of D and C, then we're in good shape. So during the exercise today, we are going to do some of this on a worked example. I want you to look at the structure contours and then to use them to make a cross section. You need to get some practice with your vertical cross section, a generalized vertical cross section, remembering to estimate the thickness of the different units involved, and then I want you to write an interpretation of the geology. Okay, thank you.